5.2 and 5.3 have the idea in them about the mean value theorem for integrals. This is the corresponding theorem for integrals that we've already discussed for derivatives. There's a mean value theorem for derivatives. There's an analogous one for integrals. But of course, where with the derivative, the mean value theorem for a derivative dealt with the idea of slope, because a derivative is a slope, here the mean value theorem for integrals will deal with the idea of area. So I'll try to draw a picture to explain what it's saying. So let's assume for a moment that we have a continuous function. There's x, and here's f of x, and f of x is continuous. It will be when I draw the picture, but it needs to be for the theorem to hold anyway. So maybe something like that will be sufficient. All right, and now we just pick an interval AB. I'll just pick it kind of randomly here. Here's A, and over here is B, maybe. Something like that. All right, so there's an area in there between the curve and the x-axis. And that, of course, is the integral of f along the interval AB. So I have the integral from A to B of f of x is, of course, the green area in here. Okay. And our interval is of size b minus a, of course, the latter minus the former. All right. So if the function is continuous, what will happen then is you'll be able to find a value c somewhere in here. Okay? And that value c is such that if you map it up to the curve, right, somewhere in here, just like there was a c for the mean value theorem for derivatives, map it up to the curve there, and there it is. So that is c comma function at c, and c is in the interval AB that we've constructed here. Right? Just like the mean value theorem for derivatives, right? You can find a c within the interval that we're talking about. And the property that that c value will possess is that this height is, of course, f of c, right there, which really means this whole height from 0, right, is f of c, whatever number that should be on the function, right, that height there. And we can now construct a rectangle whose area will be exactly the same as the area of the integral. In other words, there will be some c value where if you map it up to the curve, you can take that which is the area which is above that horizontal line, right? And you could kind of, in a sense, spill it into the area that is lacking over here from below the horizontal line. That is, you could compact the integral area between the curve and the x-axis into a single rectangle. That should always be possible as long as the curve is continuous. That's the mean value theorem pictorially. So the way it pans out in notation is, since our claim is green area is equal to red area, right? The rectangular red area should be the same as the green between curve and x-axis area. Again, if you were to in a sense, pour this leftover material above into this ditch below. It should fill exactly, would be the idea. But the green area is our integral expression. And the red area is a rectangle, so therefore it's simply base times height. Now the base is b minus a, of course. And the height is the height f of c, right? That function value where c was located. So f of c is the height, so height times the base. So therefore, the mean value theorem is telling us if f of x is continuous, again, it's a quality it must possess. If f of x is continuous on AB, this should sound very similar to the mean value theorem for derivatives. There's some differences, of course, in the phraseology, but it is rather similar. If f of x is continuous on AB, then there exists a value c, which I demonstrated in the picture, and c will be in the interval AB, such that this expression right here. Only I'm going to divide off the b minus a from both sides. So it will look like this, that the function will have a value which is equal to 1 over the displacement here, right, times the integral. So there's the mean value theorem for integrals.